All right. Today, we are diving into one of the most exciting frontiers in AI, and that's graph neural networks. Now, this is a technology that's basically teaching machines to see the world in a whole new way, not as just a bunch of separate, isolated things, but as this deeply connected web of relationships.
So let's kick things off with a big question. We've gotten really good at teaching AI to recognize, say, a cat in a photo. That's amazing. But what if it could go deeper? What if it could actually understand the relationship between that cat and its owner? Or, the invisible chemical bonds that hold together a life-saving drug? What if AI could finally truly understand connection? I mean, think about it. In the real world, things almost never exist in a vacuum, right? A person is kind of defined by their friends, their family. An atom's properties totally depend on the molecule it's a part of. It's all these relationships that give things meaning. And that, right there, is the exact challenge that graph neural networks, or GNNs for short, were built to tackle. Okay, so to really get a handle on GNNs, we've got to start with this one simple but really powerful idea. The world is a network. Seriously. From your social media feed all the way down to the dance of atoms, everything is connected. Now, in the world of machine learning, we have a special name for these networks. We call them graphs. And a graph is super simple, really. It's just a collection of things, which we call nodes, that are connected by relationships, which we call edges. That's it. Just think of the nodes as the dots, and the edges as the lines that connect them. And once you start looking, you realize this structure is literally everywhere. You're already totally familiar with it. A social network, that's a perfect example. All the people are the nodes, and their friendships are the edges. A molecule, the atoms are the nodes, and the chemical bonds are the edges. You can even think about research papers this way. The papers are the nodes, and the citations are the edges, linking them all together. Okay, so this is where things get really interesting. This is where the whole perspective shifts. Because we can start to see everything as a graph, even data that, at first glance, doesn't look like a network at all. Take an image, for example. We usually just see it as a grid of pixels, right? But what if we saw every single pixel as a node connected to all of its neighbors? Or what about text? We think of it as just a sequence of words, but it can also be seen as a simple graph, just a chain where each word is a node connected to the next one. This little shift in thinking, this is what unlocks the incredible power of GNNs. So, you might be wondering, why do we need a whole special type of neural network just for this? Well, it's because graphs introduce a really unique, kind of tricky challenge for traditional AI. It's called the permutation problem. All right, take a look at these two diagrams. To you and me, they're the same thing, right? We instantly see that they both showed the same 4 nodes with the exact same connections. The layout is different, sure, but who cares? The structure is what matters. And there's a fancy term for this. It's called permutation invariance. But here's the problem. A traditional AI, it gets really confused by this. It's built to expect data in a nice fixed order. So if you just list the nodes in a different sequence, the AI might think it's looking at a completely different network. Which brings us to the big question. How in the world do you teach an AI to see the real structure, no matter how you list the parts? And this is where our hero comes in, the graph neural network. See, GNNs have this incredibly elegant, almost intuitive way of thinking that solves this problem perfectly. The solution is this brilliant process called message passing. Honestly, the best way to picture it is to think about how gossip spreads through a social network. It's like each node gets to talk to its direct neighbors and learn what they know. And it all works in just 3 simple steps. First, each node gathers info. It just listens to the messages from its immediate neighbors. Step 2, it aggregates all that info. It just kind of combines everything it heard into one single summary. And then step 3, it uses that summary to update itself. That's really it. Gather, aggregate, and update. But the real power, the real magic, comes when you repeat this process. See, after 1 round, a node knows about its direct neighbors. Okay, cool. But after 2 rounds, it now knows about its neighbor's neighbors. And if you keep going, this super simple local conversation, just repeated a few times, builds this incredibly sophisticated global understanding of the entire network. Every single node starts to get a sense of the whole picture. So, that's the basic idea of how GNNs work. But why does it matter? Well, this simple idea of message passing is leading to some absolutely mind-blowing real-world applications. Because GNNs get connections, they're changing the game in all sorts of fields.
We're talking about discovering new life-saving antibiotics by looking at molecular structures. They're being used to power incredibly complex physics simulations. They can help spot fake news by tracking how it spreads through a network. They can predict traffic flow in cities. Oh, and they're also helping build those super smart recommendation systems that basically run a huge chunk of the modern internet.
And just to show you how powerful this really is, let's look at one amazing example. For more than 100 years, scientists have been totally stumped by this question. Can we predict what a molecule smells like just by looking at its structure? Well, you guessed it, GNNs are actually cracking that code. By treating a molecule just like a graph, atoms as nodes, bonds as edges, a GNN can analyze its structure and learn to predict its properties. So, for instance, it can learn to classify a molecule as having a pungent smell, like garlic or peppermint, and it can do it with incredible accuracy. It is literally learning the connection between physical structure and the sensation of scent. How cool is that? So, what does this all point to? Well, it leads to one really clear conclusion. The future of AI is all about connections. This quote from some of the pioneers in the field really gets to the heart of it all. When they say preserves graph symmetries, that's just a fancy technical way of saying that it understands that structure matters way more than order. In other words, it solves that permutation problem we talked about. And optimizable transformation, that just means it can learn from that structure. It's a tool that was built from the ground up specifically to think in terms of network. And so that leaves us with one final big thought. Our world is just filled with these incredibly complex, connected problems, in biology, in logistics, in social science, everywhere. The real question now, the exciting question, is what other huge problems could we solve if we just start thinking in graphs?